Welcome to the Sci-Hunter tool access portal. First, I will provide the details required to access the tool. Enter the name of the institution or company. Then select the country from where we are accessing the tool, followed by a valid email address. Please ensure that the email address is correct because an email verification link will be sent to validate the session and connect the NCBI API. Accept the agreement by clicking the checkbox and then enter the Sci-Hunter portal. This is the home page of the Sci-Hunter tool. I will switch to dark mode because I personally like it. We can access this option from the top right corner by clicking the three dots. The menu also allows us to print the page and record the screen. Sci-Hunter is an open access, freely available, automated, and highly customizable literature mining tool designed to query PubMed, extract relevant manuscripts using complex keyword logic, and perform advanced text matching to identify specific user-defined features. Equipped with interactive data tables, dynamic visualizations, and adjustable search parameters, it is built to streamline the literature review process. Please read the notes and disclaimers carefully to maximize the tool's accuracy and utility. Sci-Hunter is built upon the foundation of SHoDH, which stands for Semantic Harmonizer for Optimized Document Harvesting, a computational framework that I originally developed during my PhD program. It has been extremely helpful for identifying important protein features from large volumes of literature and also served as one of the text mining foundations of BrainProt. Although my demo focuses on a biological context with diseases and gene names as examples, but the tool is not limited to these areas. It can be applied to any research field by simply modifying the search parameters, keywords, and features. Now on the left side, we can see the search parameters. We will start with the timeline by selecting the start year and end year. For now, I will keep the default values. Next is the manuscript type filter. I will select all. When selecting journal article only, please remember that we may miss many valuable publications such as meta-analysis, letters, database papers, and other important publication types. Therefore, it is generally recommended to search all manuscript types. Next, let us adjust the maximum manuscripts to fetch. I will keep the default value for now. We can download as many manuscript lists as required. However, selecting a larger number of manuscripts will significantly increase the processing time. Please be patient while the background API fetching and deep text matching algorithms complete their analysis. Now let us configure the keywords. For the number of primary keywords, I will keep it as 2. The primary keywords will be glioma and meningioma. Although I am selecting both title and abstract, please remember that this option may retrieve some articles that are not primarily about the selected disease. For example, one of the keywords may simply appear in the abstract, while the main focus of the paper is something else. Therefore, it is always important to understand the difference between searching only the title and searching both the title and abstract. Now let us discuss the primary match similarity. With an average keyword length of approximately 8 letters, such as glioma or meningioma, in 95% similarity allows approximately 1 character to be different while still considering it a match. If we are completely confident about the spelling of the keyword, it is always recommended to use 100% similarity. Since there are no spelling mistakes in our keywords, I will keep it at 100%. Now let us move to the number of secondary keywords. Please remember that secondary keywords are searched only within manuscripts that already satisfy the primary keyword search. Optimization is extremely important here. Now let us click Run Sci-Hunter Search. The first search will be very quick because we are fetching metadata for only 100 manuscripts. We can see that the primary keywords return 6,806 manuscripts matching the base query, and metadata is now being fetched for the selected top 100 manuscripts. It is important to carefully review the search summary and results. Now let us increase the maximum manuscripts to fetch because we can see that more than 6,800 manuscripts were found. I will change the maximum fetch value to 5,000 and run the search again. This time the analysis will take longer because the tool is fetching and organizing a much larger amount of information. While the analysis is running, let us discuss a few important points. Why it is important to optimize the keyword and similarity index. For example, imagine that the word glioma appears only once in the abstract because it is mentioned as a reference, while the manuscript itself is actually focused on breast cancer. If one of our second keywords, such as mutation, also appears in the abstract, that manuscript would still be retrieved even though it is not truly related to glioma. Therefore, when we are confident about the primary keyword, it is often better to search only in the title or include multiple variations such as glioma, glioblastoma, GBM, and glioblastoma multiforme with 100% similarity to capture all naming variations. The analysis has now finished. Let us first look at the total publication trend. The plots are generated only from the manuscripts that have actually been fetched. If we want the plots to represent all the manuscripts found by the search, then we must increase the maximum manuscripts to fetch to match the total number of manuscripts found. Please remember that the start years may appear to have fewer publications because we did not fetch all 6,800 manuscripts. Since the algorithm prioritizes recent publications during fetching, the latest years may appear underrepresented unless all manuscripts are downloaded. The Venn diagrams are fairly self-explanatory. They show the number of manuscripts shared between the selected keywords. It makes sense that glioma has a much larger literature than meningioma, and we can observe similar relationships for the secondary keywords. Now let us move to the output table. Every column here is important. Since we selected 100% similarity and there are no spelling mistakes, we should not observe any lower similarity matches. The manuscript type column shows the different publication categories returned by PubMed. If a manuscript does not have a publication tag, Sci-Hunter is not responsible because the information comes directly from PubMed. Again, when filtering only journal articles, we should remember that valuable publication types such as meta-analysis, letters, and database papers may be excluded. Next, we have the manuscript title, PubMed ID, publication year, first author, and journal name. The journal name column is searchable, allowing us to quickly identify manuscripts published in a particular journal. The PubMed ID is clickable and redirects directly to the PubMed record, making it very easy to access the original manuscript. One useful feature is the serial number column. Clicking a serial number, such as 21, helps us keep track of the manuscript while navigating across different columns. All of this information is also included in the downloadable output CSV file. Now we come to one of the most interesting and useful parts of the tool. We have collected thousands of manuscripts, but suppose I have a list of specific features in mind. This is where the user list specific search becomes extremely useful. The only requirement is to prepare a CSV file containing the list of features. As shown here, we can include gene symbols, protein names, or both. Save the file as a CSV. A demo file is also available on the GitHub repository for reference. Now let us upload the file. The only limitation is that the uploaded file should not exceed 200 megabytes, although a gene or protein list will almost never reach that size. After uploading, we can preview the file. Next, select the header that contains the feature names we want to search. We may also include another column containing protein names. In some situations, combining gene symbols and protein names provides better coverage, especially when searching only a few well-defined features. For gene symbols, I recommend using 100% similarity because there should not be any spelling mistakes. Now let us click Run Feature Mapping. This analysis may take some time, so please be patient. While the analysis is running, let us discuss the similarity index. The tool uses a match ratio ranging from 0% to 100% to compare the user-supplied features with manuscript text. A 100% match requires an exact character-by-character match. A value below 100% allows small variations. However, this should be used carefully because even a single character difference can significantly change the results. Reducing the similarity threshold is mainly intended to capture minor formatting differences, such as wild type versus wild type, or small suffix variations, not to compensate for incorrect spelling. Now let us discuss the confidence score. During feature mapping, Sci-Hunter calculates a confidence score to estimate the relevance of each manuscript. Mentions in the manuscript title receive 1.5 times more weight than mentions in the abstract because the title generally represents the central focus of the study. If we are searching protein names, we should be careful and consider reducing the similarity threshold to 95%. For example, a protein such as alpha-1b glycoprotein may appear in several different formats within the literature. Sometimes Greek letters are written as symbols, sometimes words are joined together, and sometimes spaces are omitted. However, we should never reduce the similarity threshold for gene symbols. For example, HBB and HBA differ by only one letter. Lowering the similarity threshold could incorrectly match one gene to the other. Therefore, when searching gene symbols, always use 100% similarity because authors rarely misspell official gene names. A single character change can completely alter the meaning. As I like to say, one character can turn hero into zero. For long protein names, however, slight formatting differences are common, so using 95% similarity is often more appropriate. The feature mapping has now completed. Let us examine the results. The first summary table is extremely important. Feature 1 contains our gene symbols. Since we did not provide a second feature column, feature 2 is shown as NA. The average similarity is 100% because we used a 100% similarity threshold. The most important column is the number of manuscripts. Different genes are associated with different numbers of manuscripts. The total frequency column indicates how many times the feature appears across manuscript titles and abstracts. The red and green highlighting makes it very easy to identify where the keywords appear. Separate title frequency and abstract frequency columns provide even more detailed information. We have already discussed the confidence score, so instead of repeating the explanation, let me simply sort the table by confidence score. Immediately we can see that IDH1 appears at the top, followed by EGFR and several other highly relevant genes. Now let us look at the plots. The feature-specific bar plots and line plots are fairly self-explanatory. The plots may appear small on the screen, so we can simply enlarge them. Notice that we have approximately 389 IDH1 related manuscripts within the glioma literature and 77 NF2 related manuscripts within the meningioma literature. Both are well-known hotspot genes for their respective diseases. If we examine the remaining features, they also appear highly relevant. Similarly, we can visualize statistics for the secondary keywords, such as human and mutation. Looking at the yearly trend, please remember that the latest years may still appear lower if all available manuscripts have not yet been fetched. The overall trend across previous years remains very clear. These figures can be directly downloaded and included in reports, theses, presentations, or manuscripts. All of the summary tables are also available for download. Now let us look at another powerful feature called Extract Feature-Specific Manuscripts. This allows us to select any feature from our uploaded list and immediately view only the manuscripts associated with that feature. For example, I will select IDH1. We can immediately see approximately 390 manuscripts associated with IDH1. We can also search within these manuscripts by journal name if required. Finally, we can download only the IDH1 specific manuscript list. This is another example of how Sci-Hunter, powered by SHoDH, makes literature mining highly dynamic and efficient. I would also like to acknowledge the NCBI and PubMed databases for providing one of the greatest scientific resources ever created. These databases represent decades of human innovation, scientific discovery, and the dedication of researchers around the world. When we search 20 years of literature for a particular keyword, what we are really seeing is the collective effort of thousands of scientists working quietly across the globe to advance science and expand human knowledge. If Sci-Hunter contributes to our research, publication, presentation, or analysis workflow, please acknowledge the tool by citing either the Sci-Hunter web application or the GitHub repository in the appropriate section of the work. Finally, click on the GitHub repository to access additional information, demo files, documentation, and future updates. I'm continuously maintaining the tool and will be releasing many more updates and features in the coming days. For any queries or comments or suggestions or bugs, feel free to email me or text on LinkedIn. Keep exploring, and I will see you soon.